This conference will now be recorded.
So, very good evening. Today, we'll be starting a new chapter, that is nuclei. This is 13th chapter. Yeah, very good evening, Deepa. You have arrived. Very nice. Today, actually, we are starting a new chapter, that is the 13th
Good evening,
chapter,
sir.
nuclei,
Good evening.
atomic nuclei. Yeah, good evening. So, today we'll be learning few basic terms in this chapter. So, first of all, what is atomic nucleus? We had already learned somewhat, but we don't know till now how to write the composition of nucleus, and then we'll learn few definitions like isotope, isobar, isotone, etc., and atomic mass, then nuclear size, nuclear density, etc., and we'll see, if possible, we'll learn nuclear forces also. So let us start our topics today. So, atomic mass, you know, in the previous chapter, Rutherford gave a model, planetary model of like uh, atomic model which is having similarity with the planetary model. Okay, so Rutherford had explained the large angle scattering in alpha particle scattering experiment. If you remember, large angle scattering, large angle scattering was explained explained proposing the existence of nucleus. Okay, so if you remember, we had a thin foil in the gold foil experiment, and most of the alpha particle, they were just passing through, but very few number of alpha particles were returning back. Okay, so and that number was negligibly small, and that's how he concluded that these are called large angle scattering, like 90-degree or more than 90-degree. Okay, so more than 90-degree theta or phi here, phi scattering phi is more than 90-degree, are called large angle scattering, and this scattering was explained by the uh, by proposing the existence of a tiny region inside the atom which has positive charge, and that's how electrons, like alpha particle, will be repelled by that or scattered by that, back scattered by that. Okay, so anyway, we had already seen model, Rutherford's model, and that was just like planetary model. So there is a nucleus inside the atom, and inside. So far he did not know about neutron, but he was saying that it must be having some positive charges which are called proton, and same number of electrons will be there in the outer orbits, but these orbits are not stationary orbits. Okay, so these orbits are like any arbitrary orbit. So that's what was the proposal. But anyway, we had learned from Bohr's theory that electrons will be orbiting around some stationary orbits. So those things we have learned. So here, why I am recapping this, just to let you know that how the nucleus, like existence of nucleus, was being proposed. That is to explain the large angle scattering of alpha particle. Like this was carried out by fellow scientist of, like a fellow physicist of Rutherford. Anyway, so this is fine. So this is the knowledge we have from previous chapter about nucleus. Now today we'll learn about its details like composition, what are there inside. So just after this proton was or nucleus was proposed, then there was Chadwick who discovered the neutron. Okay, so who discovered the neutron? You know, there were like already hydrogen. You see, there are three hydrogen nucleus. Okay, so one H1, one H2, and then one H3. So in each cases, see the proton number positive, proton number is same. Okay, proton number is same. So if the nucleus is composed of only proton, then all of them must have the same weight, same mass, same mass. But what we see, they have mass 1 is to 2 is to 3. Okay, so this is what the clue. This is what was the clue that there must be something else in the nucleus as well. Not only not only the proton which is determining the mass of the nucleus, but there are neutral neutral entities, neutral entities which are known as neutrons. So you have in the nucleus, so nucleus is composed of neutron, neutrons and protons, neutrons and protons. Okay, now these protons and neutrons, so protons are positively charged particle. Okay, and see, if we know the details of proton, see proton is a charged particle. Okay, so it has mass mp. We write generally mp, and that mass is actually 1.6 1.672 into 10 to the power minus 27 kg. Okay, so this mass, see, if we compare with electronic mass, look, electronic mass me is 33.1 into 10 to the power minus 19, sorry, minus 31. And see, uh, if you take the ratio, you will be surprised to see that mp by me will be nearly equal to this much. Okay, this much will be the ratio of the mass. Okay, with the proton and mass, proton mass of the proton, it is the ratio of the mass of the proton to the mass of the electron. Okay, another point is this is a positively charged particle, so it must be having a positive charge. What is the charge? The proton has, actually proton has the same charge, with same charge as the electron has, but with a positive sign. See, E, we'll write E, and that is 1.6 into 10 to the power minus 19 coulomb. Okay, this is the charge. So proton and electron, they are of same charge, but electron will be negatively charged particle and proton will be positively charged particle. Otherwise, magnitude of the charges are same. Anyway, now we'll see somewhat about neutron, and say neutron actually is a neutral particle, so it does not have any charge, Q0. Okay, neutron has no charge in that. That's why it does not get deflected or does not get attracted by electric or magnetic field, whereas the proton or electron, they do that. They actually undergo certain changes in certain changes under changes in the sense changes in the motion. Okay, anyway, so this is things, and see, neutron also has mass very near to very near to proton, 1.6. This will be 49. Okay, 10 to the power minus 27 kg. Okay, this is the mass of proton, sorry, mass of neutron. This is mass of neutron, and this has zero electronic zero charges, or this is neutral. Okay, so this is about constituent of the nucleus. So this is in. So this is a brief idea about atomic nucleus. So what are there inside the nucleus? There are neutrons and protons. So proton gives the charge of the nucleus, and neutron and proton combiningly, both in combination give the mass of the whole atom. Mass of the atom, most of the mass of the atom. Because there are electrons, they have certain masses as well, but that we have seen that this, like compared to protons, mass of proton, this mass of electron is negligible. Okay, so that is what also we have done, we have seen. All right, so we'll move to, okay, let us go to this some. Okay, so now we'll see what is the composition of nucleus. So composition of nucleus, before we know the composition of nucleus, we'll learn some terms in the nucleus itself, with the nucleus. So see, we will be frequently speaking about nucleon or nucleons. Okay, so this nucleon and nucleons. So nucleon or nucleons, we can write nucleons. See, nucleon means only one of the constituent. So proton and neutron together called nucleons. They together are called nucleons. Okay, together they are called nucleons. So nucleon is what? One of the constituent. Nucleon, only one of the constituent. So either proton or neutron. Okay, they are called nucleon, and nucleons plural. That means both proton and neutron together are called nucleons. Okay, fine. Then we'll see what is atomic number and what is mass number before I go to this composition that is needed. So let me define it here. So what is mass number? What is atomic number? Okay, one more thing I forgot to explain here. Okay, so there are few more terms like nucleons over nuclide and nuclei. Nuclei means what? Nuclei means, suppose you have a particular substance, it has many atoms, so there are many neutrons. Many neutrons in a particular atom. There are many there particular substance, there will be many many atoms and many nucleus like will be there. So nucleus, this is the plural number of nucleus. That means many, like more than one nucleus is called nuclei. So nucleus of different atoms are called nuclei. Okay, together they are called nuclei. So this is the plural, plural. And nucleides, nucleides. So here also a single, a single nucleus is termed as nucleides, nucleide. Okay. Now the main points are what are atomic mass and what is atomic number. Okay, atomic mass and atomic number. Atomic mass and atomic number, these two things, they are these yeah these two things has to be understood properly. Atomic number and atomic mass. See, the total mass of proton and neutron present in the nucleus is called nuclear mass. Okay, so what is nuclear mass? First of all, we need to know nuclear mass. This is actually mass of proton plus mass of neutron. This is called nuclear mass. Okay, total, this is called nuclear mass. And what is mass number? This is the total number of proton or neutron present in the nucleus. So total number of see, if I say Np by proton, Nn by neutron. So this is the total number of neutron. Sorry, total number of neutron and proton. So the mass number is defined as, so mass number is denoted by A. Mass number. So let me, yes, mass number. Mass number is denoted by A, and it is actually mass number is the total number of neutron and proton. Okay, so look now, if we take Z as the proton number of proton, and A is the mass number, and we have seen A is actually the total number of neutron and proton, which says that this A is equal to Z plus N, total number of proton and neutron. So this is actually the whole thing. Now let us see. So mass number A is Z plus N. Okay, this is what we have learned. But if we want to find out what is N, then we can write this. Okay, we can write this also. All right, now this nucleus actually is, like, composition of the nucleus is denoted by certain number, along with, see, here will be atomic number, atomic number, number, and at this place will be mass number. Okay, okay, I'll write it here. See, suppose a nucleus has proton z proton and n number of neutron, then composition of that nucleus can be written as z here and mass number here. Okay, so this is the composition, this is the composition of a nucleus or nuclide. Okay, so this is the composition of nucleus. So if you know the z, then see how many number of neutrons are there, can we find out, because A is equal to z plus n. Then neutron number can be obtained as, this is z proton number minus z. So this is how neutron, if we need to find out, sometimes some chemicals are some elements are given, or some nuclides are given in terms of this equation. That time you have to find out what is mass number, what is mass number, and what is atomic number. Okay, I'll just take up one simple example. Suppose carbon has various, let us take this carbon atom, carbon nucleus. Okay, similarly we can take chlorine 17 and nearly 35. Okay, or we can take helium nucleus, helium 2He4. So these are the compositions of nucleus. So like you know that this you have to write nomenclature, C or Cl or He helium, and along with that Z and mass number. Okay, this is, so if I ask you what is the number of neutron in 1H1, the number of neutron will be 0. And if I say what is the number of neutron in this, so here neutron will be, just you have to subtract the Z from A. So you get 2 neutrons over here in the tritium. So protium does not have any neutron. So I'll write once again. See, the composition will be written as, this is Z and this is atomic number, this is mass number. Okay, atomic number is the number of proton or electron both. Number of proton and number of electrons are equal to Z. This is the N plus P. Okay, N plus P. So see, we had this equation for hydrogen. This is called protium. So this protium has Z1. Okay, A also 1. Then see here, neutron is 0. Okay, so in this is the simplest atom we have in the periodic table. Okay, 1H1. So this does not have any neutron. So if I give you one example, such example, like say, let us take gold atom, and its nucleus can be written as 197. This is AU, yeah, gold, and this is 79. So if you are given this, can you tell me how many numbers of proton and how many numbers of neutron is there? So first of all, see here what we have generally. You just remember this XZA. So we can find out easily Z number of proton is this much. Okay, and what is the number of neutron? We know number of neutron can be found out just by doing this. Okay, A is how much? 197. Then 79. So you'll get something like 181. Oh, sorry, 118. 118. 118. You can do the calculation and then see. Okay, you'll get 118 this many neutrons. That's why this atom is heavier than like hydrogen, all those things. Okay, so this is about composition, and I have already told you that hydrogen had. Okay, now let us go to the some interesting thing, further interesting point, that is isotope. So this is also another term for nucleus, but not for a single nucleus. See, I'll first give the example. Okay, then let me take tritium. So these two are actually hydrogen nucleus only, and see they have same Z, only one Z. Okay, both of them has the same number of proton or electron, but what is the number of neutron here? It is 0, and here how much neutrons are there? There are 2 neutrons. So in this case, look, for these two nucleus of the same atom, they have same Z. Same Z means they have same number of electrons or proton. But what is the where is the difference? Difference is that they don't have same number of neutron. That's why their mass number, you look here, mass number is different. So A tritium is not equal to A deuterium. Okay. So in this case, mass number is different. That is because of yeah, because their neutron number is also different. Anyway, so these atoms, sorry, these nuclei which have the same atomic number but different mass number. So the atoms of an element, that means from the same element, which have the same atomic number but different mass number, they are called isotopes. I had given one example. I can pick up many other examples, like say I can give you example for carbon 6 13 and 6 12. There are both varieties. So see, Z is 6 for both, but what is different is the mass number. All right, but any chemical property of any element is determined by Z, number of electrons or number of protons, because electrons or protons are the only one which will take part in the chemical reaction. Not protons, electrons. Electrons are the only thing which take parts in chemical reaction broadly. So that's why for isotopes, I'll just write the definition first, that atoms of an element which have have same atomic number, that is Z, but different mass number. different mass number. Mass number is denoted by A. So those are called actually isotopes. Okay, called isotopes. I have given you the given examples also for isotopes. Now one more thing. So what I wanted to say is that since the chemical properties, chemical properties atoms depend on depends on Z but not on A, both of these isotopes will be actually having the same chemical property. Isotopes have the same chemical property, same chemical property. Okay. And one more thing is isotopes, they lie in the same same position in the periodic table. Same position in the periodic table because they have same number of same number of like same atomic number, and that's why they have same chemical properties, and that's how they occupy the same position in the periodic table. So this is about isotopes. Now we'll see about isobars. So isotope, I'll just skip here some examples, that's all. Okay. Or with carbon I can just write this and this. So isobar, so this is with these isobars, they have, see the atoms, sorry, the nuclei having same mass number, same mass number, but different Z, different atomic number and sorry, atomic numbers, or yeah, and Newton also, different Newton numbers and different Newton numbers. Okay. So these are called isobars. So isobars, I can give you certain examples. So these are actually from different elements, not from the same element. Like in this case, see, isotopes are of same element, that's why they have same chemical property. But in this case, isobar, actually they are not of same element. Look, you can look on example. See this famous example, this is calcium 2040, and if I take another example, argon 1840. Look, in this case the mass numbers are the same. See, mass numbers for both are same. Okay. Mass numbers are same. This is argon, but their Z is different. You look here, in this case ZA is 20, so ZB is having this 18. So two numbers of proton difference is there anyway. So calcium has its own chemical properties, etc., and also argon is not. So this is about isobar, which they have actually same mass number but different atomic numbers or different number of neutrons. Okay. Anyway, so this is about isobar. Then I'll tell you about isotone. So I'm sorry. I would have, okay. Let me just write this every time it is getting erased. But I'll keep one example for this also. I'll keep one. So one important point here you have to remember that isotopes are of same element hydrogen, and here these are not the same. So argon has 40 and here 18. So this is the example of typical example of an isobar. Then isobar, isotone. We will learn isotone. What is isotone? Isotone in this case with the same thing that isotones are nuclides having the same number of neutrons called isotones. I'll just give you the example, then you can understand. Isotones like chlorine so let me take first simple example, chlorine. And another one, I'll take, no, these are not from the same. This will be potassium. Let me take potassium 19 and this will be 17. Okay, sorry, this will be 18. 18 is, so potassium is 19, calcium is 20, then argon is 18, 19 in between argon and this calcium, this is potassium. So this potassium has, see, if you just get the number of neutrons here, how many you have? This 20, and here also if you take this is also this 20. So these are actually isotones. So you have to actually sometime in the numerical they may ask you uh, to find out the number of neutron, number of proton, number of electron, etc. So if you know these definitions, basically isotope, what are isotopes and isotones, they are actually of great, like there are various applications of these isotopes we'll see. And one more important thing is with the isotope that, see, there are three types of hydrogen atom. That means isotope means there are three types of hydrogen atom. Three types. Okay. Then what is the atomic weight? Atomic weight of, or the atomic mass, sorry, nuclear mass of the hydrogen. What is the nuclear mass of the hydrogen? So nuclear mass of this hydrogen atom can be obtained, or the mass number, sorry, nuclear mass in the sense mass number can be obtained by taking the weighted average of all these three. Okay, so that is obtained by knowing the relative abundance. Let me tell you that relative abundance, so there are isotopes Okay, so isotopes will have relative abundance in the nature. Okay, in the nature. That means what do you mean by this? This means you will have more probability of getting this than 1 is 3. So this is called abundance in the nature. So if we know the relative abundance of various isotopes, then we can find out the weighted average of mass number. Okay, for that particular that element or that nucleus. Like I can like I'll just take you through an example that nuclides. Okay, nuclide. Let me tell you that chlorine has two isotopes. Okay, chlorine has two isotopes, and see relative abundance generally expressed in terms of percentages. Okay, so let me tell you this. Chlorine 1735, this has relative abundance some 75 percentage. That means probability of getting this in the nature is more than the other one. This may be 37. So this has natural abundance of some 25 percentage. Okay, so there are two isotopes of chlorine and they have different probability of getting them in the nature. So that is called relative abundance. And if we know this relative abundance, we can find out the weighted average of mass number. So average atomic mass of chlorine, average atomic mass of chlorine, average mass, atomic mass of chlorine is given by, you multiply this natural abundance with the mass number shown for this particular isotope. So 35 into 75 plus you have 37, it has natural abundance 25 percentage. So 25 and divided by 75 plus 25. Okay, so this will give you the weightage average, and if you calculate you will get 35.50. Okay, this is called weighted average of atomic masses of all the isotopes, and that would give you average atomic mass of any element which has different isotope having different natural abundances. So this is very important. Sometime I'll just give you one example. I'll just give you one example of this. Suppose, let me clean this. Suppose you have uh, boron, okay, 5, boron 5 11, and boron 5 10. Boron 5 10, and the average atomic mass of these two isotopes is given. So that is something like this. Okay. Then what? Okay, what is the ratio of natural abundance? Okay, let me just write in a short notation. Natural abundance, I'll write n dot a of B11 to B10. So this is the question. So to solve this problem, this kind of problem, what you have to remember, how do you get average atomic mass? So we know average atomic mass for this is given. So this can be written as, suppose let us take for 11, this has natural abundance x percentage, then it will be having 100 minus x percentage, right? So this is the thing. So we'll just assume and then find out the value of x. That's how you'll be able to solve this problem. Let us do that. So this is 11 into x plus 100 minus x into 10. So whatever atomic number is given here into the natural abundance, okay, and divided by. So you have to add all of them, whatever, like how many isotopes you have to add, multiplying their natural abundance with the atomic mass number of the all of these isotopes, and you have to divide with 100. Okay. So then if you just do this, if you just solve this problem, so you have 11x minus 10x plus 1000 here, and you have here 1081 on the other side. So you look here, x is equal to 81. That means you have x is equal to 81 percentage of abundance of what? This boron 11. So now if you just subtract this, so this boron 10 will be having 19 percentage then. Okay. So what will be the answer for this question? The ratio you have to take. Ratio will be 81 to 19, or 81 is to 19. So this is the ratio you'll get for this particular problem. Okay. So this is how, if you know the natural abundance, then it is easy to find out the average mass. And if you know the average mass, then also you'll be able to find out what is the natural abundance. And there will be numerical problems, as I have given here an example. So this kind of problems will be there in the exams. So now we have already learned what is isotope, isobar, isotone. Now we have learned atomic mass also. Okay, let us now learn little bit about the unit of the atomic mass and nuclear size and nuclear density. We have got few more minutes. So atomic mass, we know, like, see, if I just give you one example of atomic mass, it is very tiny. Atomic mass is actually given by, this is mass number, not the mass. So not exactly the mass. Suppose if I tell you, then you will be able to understand. Atomic mass of carbon, atomic mass of carbon, atomic mass of carbon carbon 12 is actually is 1.92678 into 10 to the power minus 26 kg. So see, this is the typical amount of mass, see how much less it is, like how less it is, 10 to the power 26 minus 10 to the power 26 kg. Look, this is very, very small. See, I can say half kg, 1 kg, 2 kg, that is fine. But is it feasible? Is it feasible to express the atomic mass of any element with this unit kg? Is it feasible? No, it is not that great. Because see, this means, like you just measure 1 centimeter length with maybe some 100 centimeter with 100 centimeter scale. So kind of that. You have to suppose this is 1 centimeter. Okay, it will be measured. You can measure it, but it is somewhat very, what to say, wizard thing. Okay, so and the measurement also will not be so proper. So if you have a scale smaller than this length, like see if you have this much scale, then you can just add all the readings and then get the total length, right? I mean to say that if you have a quantity, that particular quantity, whether it is mass, length, or whatever, you should use a smaller unit to, like appropriate unit to express that quantity. Like here in this case, 10 to the power minus 26 kg. This is very, very less quantity, minus 26. But is it feasible to express it with kg unit? It is not. So that's why there is a new unit system for at this nuclear physics. So there is called atomic mass unit. The atomic mass unit, it is defined as, see, one atomic mass unit is defined as 1/12 of the mass of carbon 12 atom. So it is just a definition. So 1/12 of the mass of actual mass of excuse me, 1/12 of the actual mass of carbon is taken as one atomic mass unit. And I had already told you the amount of the atomic mass unit. This is the 2678, something like this, was the atomic mass of a carbon atom. So if I take 1/12 of this, then you get one atomic unit, and it is expressed as one. So atomic mass unit, we can write one atomic mass unit, so it can be written as AMU, or sometimes simply U. 1U is given by 1/12 into this factor. Okay, this factor. So into 10 to the power minus 26. So it will give you a number of this. 27 kg. So we sometimes use up to this 1.66 into 10 to the power minus 27 kg. Okay, and see any mass, like say you have electronic mass. So electronic mass is something like, see, mass of electron is this, no? So 9.1 into 10 to the power minus 31 kg. So this can be expressed in terms of atomic unit if you just divide with this mass. You just divide this, then you will get how much atomic, in terms of how much, like in terms of atomic unit, you can express this particular mass. So it is given like this. Even in this unit also it is very, very less. Okay, AMU. All right, so this is atomic mass unit. Now atomic mass unit can be expressed in terms of this is kg, but in terms of energy unit also it can be expressed. So according to Einstein's mass energy equivalence, any amount of rest mass can have this much energy. This is called rest mass energy. Rest mass energy. Any amount of mass m can have equivalent rest mass energy, that is E is equal to m into c square. So mass of the object multiplied with the square of the speed of light in the vacuum. Okay, this is called mass energy equivalence equation given by famous scientist Einstein. And in nuclear physics we have lot of uses of this particular equation. So we'll see this particular mass can be expressed in terms of MeV. Nuclear physics is called high energy physics, or particle physics is called high energy physics, because here the energy range is mega electron volt or millions electron volt or millions to trillions and all. So that's why this field of nuclear physics or particle physics is called high energy physics in high energy physics. So one atomic unit is 931 MeV. So this calculation can be done by using E is equal to mc square. M you can write in terms of kg and C in terms of 2.998 into 10 to the power 8 meter. That means whatever you know, 3 into 10 to the power 8 meter per second. Okay, so if you put this in this equation, plug in this equation, so this particular 1 mu, so this mass, okay, let me just do it. So 1 u or 1 mu is mc square. See, it has equivalent energy unit is equal to mc square. Mc square, if you just put this into 10 to the power minus 27 kg into c square. C square means you write 3 square into 10 to the power 16 meter per second. So if you write this in terms of, okay, now you get this in terms of joule, then you can divide this with 1.6 into 10 to the power minus 19 joule. Okay, so this will give you electron volt, and in fact you will get 931 MeV. Okay, so today we'll stop it here with this. Next day, so we have learned up to atomic mass unit. What is atomic mass unit? This is the unit defined for expressing very tiny mass, like electronic mass is of the order of 10 to the power minus 31. Then proton, it has 10 to the power minus 27. So this much less mass cannot be appropriately expressed by kg. So that's why atomic unit is a new unit which is being defined as 1/12 of the mass of carbon. Okay, mass of C12. Okay, and that can be expressed in terms of MeV, electron volt. And see, you will get one atomic unit means in terms of energy you will get 931 MeV energy, and this we can obtain from E is equal to mc square, that is the mass energy equivalent equation given by Einstein. What does this mean? Any amount of mass m at rest can have this much equivalent energy mc square. Okay, so this is how, if we calculate, we get 1 u is equal to 931 MeV energy. So Deepa, if you have any doubt, you can ask me now, or otherwise we'll stop it here. This is a very simple. We have learned few definitions, one or two numerical we have done. So now next day we'll take up nuclear size, nuclear density, nuclear force, and binding energy, mass defect, etc. So this chapter is very, very important and interesting, and most importantly, it will be very easy to answer various numerical problems from this chapter. So overall, it is important for competitive exam. So I'll stop it here. Deepa, if you have any doubt, you can ask me. Okay, if you don't have any doubt, I'll stop it here for today. Bye for today.